Very excited today to have Andy Ko from the University of Washington. Andy works at the intersection of human-computer interaction and education and software engineering, I think. Andy has done really exciting work in those areas, received numerous Best Paper awards, and comes to us today to talk about learning to code. So take it away.
Great, thanks a lot, Matt. Let's do a quick AV check. Can everybody hear me in the back of the room? All right? All right, good. I will stand right here and I won't move. So thanks a lot for inviting me. I thought I'd give a bit of background about myself before I dive into the topic, partly just to explain why I'm studying this topic instead of some of the things that I've studied in the past. So you have some context for why I pivoted. So this is a bit about me. I've been a professor at the University of Washington in Seattle for about the past 10 years. I did a Ph.D. at Carnegie Mellon at the HCI Institute. This was between 2002 and 2008, and so I was one of the first classes that graduated from that program. And I have a pretty interdisciplinary background. I did an undergraduate in computer science and psychology, and then at CMU I spent most of my time taking design courses too. So I tend to think of myself as somebody who's pretty mixed in backgrounds. I don't think of myself in a strict disciplinary way. And that means that I like to do a lot of research on very applied problems that bring together all of those perspectives. So the particular problems that interest me really all center around code. Code fascinates me for lots of reasons. So one of the things I like to say is that it's the most powerful yet least usable user interface we've ever invented. We can create almost anything with it, but almost nobody can create anything with it. Right? It's in a weird tension because it is this powerful thing and there's so many people that want to learn how to use it, but we can't figure out how. How do we empower them to actually do it? And in my view, I sort of view this as a social justice issue. If everybody that wants to code can't, how do we deal with that? Everybody wants to do it, and they should be able to harness this power, but there are all of these immense barriers to them doing that. So I actually spent a good chunk of the beginning of my career focused on making code more usable by trying to create more developer tools that would lower those barriers to people accessing this power. By helping them read code more effectively, write it more effectively, test and verify and debug it more effectively, and did a lot of HCI techniques to make interactive developer tools more successful at lowering those barriers. All the while, I sort of realized while I was doing this that tools were only part of the picture, and I sort of understood this, but not in a very intimate way. And so what really changed was I went off for 2 years or so, and was CTO of a startup that I co-founded. And I managed a team of up to 10 developers at any given time. And one of the things I realized was that while I was mentoring those engineers, skill was always more important than speed. And this manifested in a couple of different ways. I could give a tool to a developer, and if they didn't have the skills to use it correctly, it wouldn't really help them. Sometimes it would hurt them. The skills that they needed to use tools effectively really only came from learning, and I had to provide that learning. Learning comes from teaching, right? So I spent most of my time as a manager actually teaching my engineers the skills they needed to be successful engineers and successful users of the tools that they were using. And really, learning was at the heart of it, and ability was at the heart of it, and it wasn't really tools that was determining whether or not people were successful. So while I was in startup land, an exciting thing happened that eventually led me to pivot and start focusing more on learning rather than tools. And it was that the world just decided over in the past decade that it wants to learn how to code. So let's walk through some of this history just in case you don't know it. There were things like Mitch Resnick's Scratch at MIT in the Media Lab that really exploded, and we suddenly had tens of millions of people in middle school and high school using Scratch to creatively express themselves. The CS Education Week, which is actually this week this year, so yesterday was the kickoff to that. So now you have something like 50 million kids across the world doing hours of code in schools, teachers teaching computer science in middle school and high school this whole week. People started practicing skills around coding and computing online with things like Coursera and Khan Academy. Code.org, which is a nonprofit based in Seattle, founded by Hadi Parsovi, started advocating for computer science in every US school, just offering it, not requiring it, but allowing students to access it if they wanted to. The UK, Korea, and New York City started offering CS education in every K through 12 school in all of these districts and countries, and that's still unfolding as we speak right now. Bootcamps like Ada Academy and about another 100 across the world started popping up to teach people a lot of these skills outside the context of universities. The White House and President Obama announced support for nationwide computing education access in K through 12 public schools. And so when you have the president of the country saying everybody should learn this skill, or everybody should have the right to learn it, and the access to learn it, that's a pretty significant moment in a country's history. And then more recently, just a few months ago, major companies announced about $1.3 billion in funding to actually support that initiative that the previous White House leadership announced. And so we're at a time right now where not only do millions of people actually want to learn this skill, but we may actually be able to provide it to them if they want it. That's a pretty amazing thing. So the big question here to kick this off is, are anybody in these programs, in these classes, actually learning anything? There's access now, and some people are using that to try to learn. Are they succeeding? We don't have a lot of great data on this, so we have to speculate a bit about what some of this data means, but I'll present it to you and you can be the judge. Code.org has this code studio environment that's online that is used for a lot of their hour of code activities. It's also used by a lot of middle school and high school teachers to use the Code.org curriculum. It turns out that only 77% of visitors complete about 0 to 2 puzzles in this platform. And these puzzles are very, very simple puzzles. They do not involve a lot of complexity. So, and this isn't not just people going on the web and finding this. This is in classrooms with teachers teaching them for long periods of time. This is how far students get in these classes. Another signal. There's record enrollment in advanced placement computer science courses. There's 2 of them now, APCS and APCS Principles. So both of them are just now the most popular APCS exam that exists out of all of these, which is kind of amazing. But most don't take the exam who take the class, and 60% of those who do take the exam fail it, meaning they get a 1 or a 2 on a 5-point scale. And in underrepresented minority groups, about 90% fail the exam. That's also not a very encouraging sign. If you look at boot camps, there are about 23,000 adults in the United States across 95 coding boot camps over the past couple of years. Only 24 of those report dropout rates, and those that do reported rates of 10 to 15%, with a median of 45%. So they last about 2 or 3 weeks before they decide, I can't do this, and they leave. That's also not very encouraging for programs that are 6 weeks to 12 months, that quickly people leave and give up. If you look at MOOCs, we know these numbers, only about 10% finish MOOCs that are related to computing and that involve some programming. And studies that look into why people leave, it has a lot to do with the same people that students leave computer science courses in universities. It's hard and they don't get it, and so they stop. It's not just about engagement or motivation, it's also just about the instruction. And then one last statistic here. There was this survey last year of lots of different types of employers, a fairly representative sample. 62% of employers view applicants to entry-level developer positions as lacking basic programming knowledge. They hire them anyway, right? So we still get all of the really great statistics about our placement of our graduates. They'll take them, but they don't meet their expectations. So by all of these measures, computing education really isn't working that well in really any context. And these are sort of cause for concern that learning is actually happening. So I did some reading, tried to understand what we already know about learning of computing and programming. I read a lot of seminal literature in learning science and education. I read the relatively brief 30-year history of computing ed research literature. There hasn't been that much published on the topic. This is in venues like the ACM International Computing Education Research Conference, which started about 12 years ago. There's a journal, there's the CXC conference. And generally, there's 6 major discoveries from that literature that I found that are kind of a foundation for understanding this. 1, people find computing boring, solitary, and unwelcoming. So these are really the inclusion issues that are at the heart of why people don't learn. And then the rest of them are really sort of content issues. So people struggle to learn their first programming language. Because they don't learn that well, they can't really do anything else. People struggle to solve programming problems. So this is the process of actually taking some ill-defined or natural language description of some problem and then turning that into a working program. Nobody learns how to do that successfully. Teachers struggle to teach these things, and a lot of teachers, surprisingly, blame learners for this failure to learn, and so a lot of students lose confidence and quit. This is the basic dynamic of what happens in higher education. One of my big questions is this same thing happening in a lot of these other contexts? So I got motivated to try to address some of these problems through some research. and really wanted to focus on these two problems in particular. The second one of people struggling to learn their first programming language, and the third one of people struggling to solve programming problems. Wanted to understand why these are hard things to learn. Why is it that the way that we teach them is not succeeding? And what are some effective and equitable and scalable ways for people to actually learn these skills so they're not the reason that people give up trying to acquire these skills. So I'm going to talk about three things, a few studies about why learning to program is hard in some of these other contexts. And then I'll talk about making programs easier to read and making them easier to write in a learning context. And I'll present some early theories about why these are hard and then some ideas about how to scale the learning of them in equitable ways. So let's talk about this first set of questions around why learning to program is difficult in some of these contexts. I'll talk about three studies in three different settings. So here's one setting. For the past 2 summers, I've been working with our university's Upward Bound program. This is a program that's a federally funded program for serving first-generation college students to do college prep to get into college. And as part of that, I've just been teaching in their summer curriculum, a computer science course, to a lot of adolescents, and I've worked with about 70 Puget Sound teens over the past couple of years, all genders, all races, all socioeconomic statuses. That's the nice thing about this program is that we get everybody, we don't just get the ones interested in the topic. Here are some of the highlights of some of the things that we've been learning by working with these groups from a content perspective. So the first big important discovery is that many teens just simply lack any form of feedback or support about their learning from teachers or family members at all. They take an APCS course and they get no feedback at all. So here's one student talking about his brother. He didn't spend much time with me to be able to understand my problem in the class or unable to help me on it. Throughout the AP class, I would cry myself to sleep in silence without letting my older brother know my struggle. And this was representative of what most of the students experienced when they were taking a computer science class in high school. So difficulty without support or feedback. Some teens managed to survive this because they had informal computing mentors who provided encouraging instruction and feedback. And when we looked at how this was correlated with interest, it was really the only thing that correlated, and it explained about 80% of the variance in interest, having somebody that was supporting your learning. And so teens really sought these kinds of mentors. They sought teachers and siblings and friends of all kinds who wouldn't judge them for their failures, who would inspire them to learn, and who actually had the expertise to guide them. One fun story is that one student was setting up some Minecraft servers and didn't really know what he was doing and stumbled upon another kid in a forum who was a year older. He was just some random kid in Canada who was a year older than him, and that kid decided to mentor him over the course of 2 years over Skype to learn Java and how to set up Minecraft servers with Java. This is what allowed the kid to actually get the feedback he needed to learn all of those skills to survive in his APCS class. So that's kind of a glimpse of what's happening in one little snapshot of high schools, at least in the Puget Sound region. When we go to boot camps and look at what's happening there, this was a second study by my student Kyle Thayer, up there on the left. He interviewed 26 boot camp attendees that had attended about 10 different boot camps in the Puget Sound region, and just tried to look at their experiences in the boot camps, before, during, and after they had participated in them. And here are a couple of snapshots about their experiences. Some boot camps were inclusive and encouraging, but most really offered, again, no instruction or feedback. Here's one quote that was representative. So they're trying to get you into this mentality of you have to read all of the documentation. They sit back in the background to let the students read the documentation, and what annoys me is that I paid a lot of money so that I could have somebody there to teach it to me, but all they're getting is content. They're just getting documentation. Another idea here was that many boot camps offered a really unwelcoming culture for learners that didn't have sufficient prior knowledge. Here's a quote. It was divided, the class. Those with experience, I think they were looking down at those of us without experience because maybe there were certain things we were supposed to know and we didn't. So this is a sign that the way that the curriculum was set up expected a certain level of prior knowledge, and if you didn't meet that, you just didn't get to engage or participate. The last setting I'll look at briefly here is online learning, so things like coding tutorials and other things without a teacher. And this is a study that I did with Ada Kim up on the left, not my student, but I collaborated with her on it. And she analytically evaluated 30 coding tutorials against 4 major principles from learning science. And the principles were these. One, you want to connect instruction to prior knowledge in a way that those boot camps weren't. You want to organize declarative knowledge, the facts of a discipline, of a content area. You want to help somebody understand the structure of those and how they relate to each other. You want to offer personalized feedback on practice, so when somebody does something right, they know it, and when they do something wrong, they know it and know what to do to repair their behavior. And finally, you want to foster self-regulation in problem solving, so some awareness of what you're doing and why and what strategies you're using and so on. So Ada took 30 of the most popular tutorials online, and spent about 100 hours completing all of them and judged every lesson against each of these principles. And the punchline here is that they didn't really meet any of them. There was no connection to prior knowledge in any of these tutorials, no organization of any of the declarative knowledge about programming languages or programming tools. There was no personalized feedback on program correctness or errors. Whenever somebody would make a mistake, they wouldn't learn about it or where it had come from. And there was no instruction on how to solve programming problems. It was just, here's a problem, solve it. And that was it, without any support. So one of the interesting side effects of this is that Ada, not having known how to code before she did these 30 tutorials, really didn't know anything more after those 30 tutorials. She knew a little bit of syntax, that was about it, and she knew how to copy and paste things from the tutorials into boxes, and that was the sort of extent of her learning. So why is learning a program difficult? Few of these contexts, whether it's higher education or any of these other settings that I just talked about, are actually teaching programming. There are many opportunities to read programs and to write code, but learners are rarely receiving any instruction about how to do that or feedback on how to do that correctly. Yes?
Does the previous study include platforms like Code Cognition?
Yes.
So, because they provide like personal feedback on if you have the right code or wrong code.
They certainly tell you whether your program is correct or not.
So,
That's
what do you mean by the number 3? Is it talking about, what do you mean by personalized feedback?
So when somebody writes an incorrect program according to some set of requirements in Code Cognition, it can say that the program didn't compute the right thing, right? But the reason for that is there are a whole range of possible defects that somebody injected into their program. And the reasons for those defects could be a whole range of different misconceptions that somebody might have about the programming language, its semantics, the problem that they were trying to solve, and so on. Personalized feedback would actually drill into those causes of the mistakes that somebody made and give them instruction on how to change the way that they were writing their program and change their understanding of programming and the language to avoid those defects in the first place, right? Whereas the only shallow instruction given on something like Code Cognition is your program is right, your program is wrong. Imagine a teacher that only ever told you that, right? A good teacher will tell you why it was wrong and what the correct answer looks like, and try to figure out why you misunderstood something that led to a defect and so on. That's the kind of instruction that somebody needs to learn. So if it's true that none of these media are really teaching programming, they're just exposing people to content that allows people to give themselves feedback about programming, the big question here is how can we equitably and effectively scale a lot of that instruction and feedback on programming languages and programming skill? And why do we have to scale it? It really comes down to things like we have 100,000 people in the world, 100 million people in the world that want to learn this skill right now. And we only have something on the order of about 10,000 teachers. We cannot scale the number of teachers in the world that do this. It's a very small population of people that want to teach it, and the moment somebody is capable of teaching anything about programming, they just go work for a software company and make 4 times as much money, right? So there are some challenging economics around actually preparing teachers to teach computer science. I care about that initiative too, and I work a lot to try to make sure that that teacher training is happening in some of the impact and service work that I do, but in research I think that we also have to think about how to scale that learning. So the first chunk of work that I'll talk about is about really making people understand programming languages and even just being able to read programs in a programming language and understand how they execute. So I'll give you one theory and a few ideas about how to do that and talk about some of the research that we've done for this. Here are some of the theories that exist already about why understanding programs is hard. For about 30 years, people in computing education research have argued about which programming language is the right language to learn. It turns out that really there's no evidence that this matters all that much. Static typing and syntax and errors can matter a little bit, but they only matter a little, tiny bit. When you actually find statistical differences in really carefully controlled studies, we're talking about effect sizes that only explain like 5 to 10% of the variance in people's success. A lot of people argue about which IDE or text editor you should use. If you look at things like blocks editors, there's been a lot of success of learners using those in Scratch and other environments. But it turns out relative to text, drag and drop blocks editors, they reduce dropout because people don't fail immediately. But they don't really improve learning of programming language semantics. They're really just an editor. They don't do anything to help somebody understand how programs execute. And then a surprising number of teachers believe that people don't understand programs because they have the wrong biology. There's this deep belief in this geek gene that somehow explains which people do and don't understand programs, which seems insane, but it's a fairly ubiquitous opinion amongst a lot of CS faculty. I shouldn't have to say this, but here's some nice work from Elizabeth Petitsis who shows that there is no evidence of a geek gene, and that every belief around bimodal distributions of grade distributions in classes is so wrong that actually faculty look at distributions, say they're bimodal even though they aren't, because they have this confirmation bias. And so there's these really fundamental theories that are kind of ubiquitous that are almost all wrong about why programming is hard. So our theory is just that it's the wrong pedagogy. We don't teach it in the right way. This is not a surprising thing if you know anything about learning science. Most content areas of learning require carefully designed pedagogy for successful learning. So here's our new definition of programming language knowledge, and we'll derive a pedagogy from this. I argue that knowing a programming language means being able to reliably and accurately predict an arbitrary program's operational semantics without the aid of a runtime environment. So this basically just means you should be able to read a program and know what it'll do, precisely, act as the computer, right? And you also have to know how syntax maps onto these semantics. You have to know that a particular grammatical structure in a program will result in a particular behavior. And if you know that, that's what knowing a programming language means. I'm excluding a lot of other complex things like design patterns and architectures and tools and norms. That's all important to learn too. This is just on the ability to read a program and know what it'll do. So here's an example. Knowing a JavaScript if statement like this one means you know that there's a condition that's evaluated, and then if it's true, the stuff in the first curly brackets are executed and then the second set skipped, and that if it's false, the first set skipped and the second set is executed. Turns out that most students that take an intro programming course leave that course not understanding that fact. That's just a piece of knowledge that they don't get because nobody ever teaches it to them. So knowing an entire programming language means knowing all of the semantics for everything in a language's grammar. In JavaScript, that's about 90 non-terminals in the grammar, each with its own semantic nuances. And if you look at any sort of CS1 curriculum, I'll just pick on our own at the University of Washington. The first homework is to write a Java program with function declarations, function calls, string literals, and none of the lectures explain how functions, function declarations, or string literals work at all. And if you watch where students learn this, the really resourceful ones go to their peers in the lab, and the peers teach it to them. And that's where they learn it, sometimes, right, if they're good teachers. And so most of them fail. There's lots of ways you could teach some of this knowledge. You could teach them the formal semantics. That's obviously not right. Don't give them a bunch of math. It's not going to teach them the syntax, and they have to learn another notation, and yet somehow in many universities this is what they do, most notably Cambridge and Carnegie Mellon. You could explain it via natural language. Here's how these languages execute. This is a weak mapping to syntax. You could have people write programs. This is what most computer science programs do. This requires learners to infer the semantics because they write a program, it doesn't do what they want, and then there's this big inferential gap of, I wrote all of this code and it doesn't do what I want. What does that mean an if statement does? Right? That's too big of a leap to make. And then you could have them walk through a debugger and step line by line. The problem with line by line execution is that it masks the semantics of things within a line. If you have some expression that has, let's say 12 different things happening in it, you're not going to see any of those execute. You just see the result of that line. So how should we teach semantics? We want to teach a notional machine, show each step of semantics and their explicit effects on the program's behavior, on the program counter, on the call stack, on memory, and you want to map the semantics to a concrete syntax, creating some association between syntax and the side effects it has on a program. So there's 3 ideas that we've had for this over the past few years. The first one, I'll admit, we didn't have this theory, so we didn't design it from that theory's perspective, but it led to that theory. So the mapping here is kind of weak, but I'll show you it as a sort of glimpse into what led to it. And this was work done by my former PhD student, Mike Lee. Excuse me. And the idea here was that learners discover through semantics through debugging. And so the premise here was there's this robot, and he knows how to execute programs, but not how to write them. So it's your job to help them figure out what's wrong with the programs. So it's framing coding as a collaboration between a person and a computer. And you would give a learner a sequence of debugging puzzles, and then expose syntax and semantics to them, seeding defects in the levels that they have to fix. And so this is what the game looks like. This is Gidget and all the animals he's saving from this chemical spill. And there's this little tutorial, there's a little code editor on the left, and program output in the center, which is Gidget and the things moving around the world, and then a runtime state on the right. It's a basic, full-featured IDE in the browser, completely web-based. And so the thing I want you to focus on is where the semantics come in. So here's an example. In the very first level, there's contextual help like this that helps explain what a function is. This is a level 20, so it's teaching functions after teaching many other foundational things. So here there's basic instruction embedded in the environment that people can stumble upon and read and encounter, and generally learners do when they get stuck. They use this contextual help. There's another source of instruction here where Gidget, the robot, will explain things like, there are these function calls that I have, and they have these parentheses after them, and when you call them, things happen that are useful. And so there's some semantics exposed in what Gidget's saying. And then there's also some IDE instruction, like here's where you might find out what functions you can call. And so here's a little prompt to say that if you click on an object, you can see their functions. And so that'll be visible in a sec. And then in the IDE, you'll see this green line as the program's executing, moving at a token level to show the effect of each single one of those tokens on program execution. And so as the program executes, Gidget explains each of those steps of what's happening in the program. And you can see on the right that runtime effects from that executing. Gidget reminds the reader again to view the functions. So he warned, you should look for these, and now he's saying, okay, go look for it. And so the user clicks on the button and sees that there's this function called open gate. And then they execute the program, and you can see in the upper left there's this function called open fence. And then we stumble upon this runtime error, which is, I don't know, some function called open fence that doesn't exist anywhere, right? And so by now the learner should understand, okay, calling a function means having to match a name, and it has to match the names in the object function list, and this object doesn't have a function named open fence, it has one named open gate. Maybe if I change it to open gate, that'll work correctly, right? So you can see how this is all exposing semantics, but not necessarily teaching them. So the player notices that discrepancy, changes it to open gate, and then they can step through after this and observe the effect of that. So here they say, okay, open gate, I'll go change that function call to be open gate instead of open fence. And then when they step through the program, it goes to the button, asks the button to open the gate, and the button starts opening the gate. And so that's one example of how some of those semantics get exposed in Gidget to learners. There's a lot of other things going on in this game that we didn't talk about here, but I'll summarize some of the studies that we've done on this and their effects on learning. So 4 controlled experiments with somewhere on the order of about 4,000, 5,000 players online recruited via Mechanical Turk. Learning is twice as fast as Code Academy, and twice as much as open-ended creative exploration like something like Scratch. And so this is because when we looked at some of these effects on where people's attention are, they're looking at those semantics and using that to build a robust understanding of how the language executes programs. Unlike in Code Academy and unlike in something like Scratch, where there's no instruction on semantics. There's effects like if you add assessments of semantics in the middle of these levels and reinforce that understanding, it increases learning efficiency even further. People learn about 50% faster than without those assessments. Things like drawing in attention towards the instruction of semantics by giving the compiler a face and using personal pronouns like I and you and we draws attention to those little speech bubbles. They actually read them because there's personification going on. And that doubles learning efficiency because they're actually paying attention to the instruction, whereas before they kind of ignore it. So those are some nice findings, and then we've had about 20,000 people play via word of mouth, including Chicago Public Schools and many retirees, apparently including my mom. She stumbled upon the game somewhere and decided to play it. And this has directly impacted lots of things. So Code.org has made a bunch of changes to Code Studio based on a lot of these results, and Apple's Swift Playgrounds, which teaches the Swift programming language, was based on Gidget. And so a lot of the ideas around how to provide instruction are now embedded in something that's reaching about 10 million learners around the world. So that was our first kind of jump into some of those ideas. The next one was a much more explicit attempt. This is Greg Nelson's work on teaching the semantics directly, rather than just exposing people to semantics. So his idea was, let's take all of the semantics and convert them into an interactive textbook that somebody reads before they start writing programs. And each chapter provides an example program and a tour through its execution, and then every step is reversible so that there's instruction level granularity that people can move forward and backwards through to understand cause and effect. And then they can do some causal inference on what those effects of that syntax are. So here's one of the lessons on if statements, for example. There's some high-level conceptual instruction on the left of semantics about what if statements are. And then it moves on to moving through an example program where you can observe that conditional executing. So here they start pressing next, and they can get a reminder here to keep on executing the program and reading what's happening on all of these panes in the tutorial. And then on the right, there's state, which teaches the semantics in a runtime context. And it says, we're right at this step of the conditional, we're about to execute this conditional expression to decide which way that we should go. Then the lesson goes back and teaches each component of conditionals, such as the conditional and the if block and the else block and so on. It makes all of those decisions that the program is making explicit rather than implicit. Then if a learner misses some of those explanations, they can always reverse execute, so they can go forwards and backwards through that instruction and through that program execution to re-see what they observed and go back and forth. We'll often see a lot of learners just toggling back and forward to see cause and effect, just to see what the change was in response to one step of that program. And then finally, the lesson takes it back to the conceptual level and explains the side effects of the semantics before proceeding to another example, saying things like, x has a new value now because the condition 10 is greater than 0 is true, and you can see that value on the stack. So here it's all about tying concepts to syntax to runtime state changes. So this was really non-trivial to build. We had to build a custom language stack, runtime, and we had to really capture all of the provenance of all of the compiler and runtime state to facilitate reversibility and embedded instruction for each of these steps. There's no way you can use a compiler that's built for regular use to do this type of teaching. So it's very hard to implement to make work, but it was worth the effort. So we did a big experiment where there was a 4-hour controlled experiment with about 40 intro CS students and measured learning with a standardized validated assessment of CS1 learning. And with this compared to Code Academy, learning gains were 60% higher than Code Academy. So much higher and more notable than most learning interventions that happen in any kind of learning science context. There were no low performers in the PL tutor group on their midterm that happened 4 or 5 weeks after this intervention, and the learning gains of the PL tutor group predicted the midterm grades, unlike for the control group. And so if you think about these distributions, it basically brought all of the people who were failing to learn up to everywhere where everybody else was. Unlike the control group, which just had a big scattered, highly variable learning outcome performance. So there's a lot of exciting future work that we can do here on engagement and content. I kind of imagine a whole ecosystem of language tutors that make it trivial to pick up new languages. One of the interesting implications of something like this is that you can learn all of JavaScript in 4 hours and get close to mastering it, rather than having to spend a whole 10-week course doing it, or a 15-week course. So imagine we optimize these and we get it down to like a couple of hours. You could pick up any language and maybe even make it less by building upon other knowledge people have from other languages. Last idea here on reading. Both of these were very much focused on sort of challenging learning technologies to build that would provide more robust knowledge. My new student, Benji Shea, he was interested in really low fidelity, easy to adopt strategies that would improve learning of some of these skills. So his idea was when learners have a really brittle knowledge of semantics, they often guess how programs will execute, and that's how they fill in gaps in their knowledge. Why don't we give them an explicit strategy for reading programs instead of guessing, and see if that helps them outperform guessing. So the strategy is really simple. That's all of it right there. It basically boils down to pretend to be the computer. So it says read the question, make sure you understand what the program is the prompt is asking you for, figure out where the program starts executing, evaluate each line according to the rules of Java, and then from the syntax determine the rule, follow the rules, update the memory tables based on those rules, and so on. So again, it's just moving them through the motions of being the computer. And then this is the result of all of these annotations on a piece of paper from one learner. They have a memory table and they mark their way through the program and they just precisely and systematically go through executing it. So the outcome here was pretty straightforward. In a controlled experiment with just 15 minutes of practice on this strategy, students had 15% higher performance on the problems in the lab, almost a grade point higher on the midterm. That was a writing-focused midterm, so it transferred to those writing skills. And in the experimental group, there were no midterm failures compared to 25% in the control group who failed the midterm. And so this was just from 15 minutes of practice, right? So this is a really simple and adoptable strategy for helping with some of those challenges. So making programs easier to read, all of this evidence points to just requiring learners to directly observe semantics and map them to syntax can improve learning outcomes. Of course, this is just reading programs, right? This is not doing anything more sophisticated than that. So what about the skill that we all care about, which is writing programs to do useful things? This is a harder one to try to teach and a harder one to learn. And I'd argue that we actually don't understand it very well. So there's very little prior work trying to theorize about what program writing actually is. Most prior work compares experts to novices and shows that novices are unsystematic or speculative or ineffective. There's a few papers that show that more expert developers self-regulate their problem solving, and the more productive they are, the more self-regulating they are. And so what we try to do is define a theory of programming around self-regulation. So let me give a quick primer on what self-regulation is. This is from educational psychology. This refers to the ability to reflect on and critique and control your thoughts and behaviors while you're problem solving. So this is things like planning skills, monitoring your process, monitoring your comprehension of ideas that you're using, reflecting on your cognition, self-explaining decisions that you've made and beliefs that you have about your work. So these are fairly abstract things that are not tied to one content domain. So what my student Dostanai Laksa did was build a theory around these abstract things and try to embed it in the context of programming. So he sort of views programming as involving 6 key activities: interpreting problems, searching for similar problems, searching for solutions to those similar problems, evaluating solutions to those problems for their fit to the problem you're solving, implementing solutions, and evaluating implementations. Note that only one of those is actually writing code. The rest of them are all about trying to understand solutions to problems. And then tied with that is a couple of key parts of knowledge and skill. So you need a repository in your head or on the web, Stack Overflow, cough cough, of problems and solutions that exist, right? And then you need self-regulation skills to bind all of these activities together. You need self-regulation to choose which strategies you're going to use to do all of those 6 activities. You need self-regulation to decide when you're going to shift from one activity to the next. You need self-regulation to decide when you've successfully evaluated your implementation and you can stop. Right? All of those require thinking about your thinking to successfully do. So the first thing that Dustin and I did was try to figure out, is it true that self-regulation really is related to some of these problem-solving successes? So we observed 37 novices in CS1 and CS2 writing solutions to several programming problems, and then having them think aloud. And what we did is that we observed that think aloud and categorized all of their different types of self-regulation. And the bottom line here is that most novices are engaged in some form of self-regulation, but very infrequently and very superficially. And that the more they did it of all of these different kinds, the fewer errors they made, but only when they had sufficient prior knowledge to actually solve the problems. So this is fairly consistent with this theory, that you have to have the knowledge, And assuming you have the knowledge, the more you self-regulate, the more successful you'll be at actually solving the problems. So that's encouraging. So his next question was, well, can we actually teach these self-regulation skills to improve people's programming and problem solving? So we brought in 48 high schoolers that had no prior programming experience, and we taught them HTML, CSS, JavaScript, and React in a week. These were half days, so 4 hours at a time. That's a lot to learn in a week, right? That's a crazy amount. But we figured this would be a good stress test of this theory, right, about self-regulation. And then we had them build personal websites using all of those skills for another week afterwards. And the only difference between the control and the experimental group was that the treatment group received two things. They got a lecture from Dostani about his theory of problem solving in programming, so they had some kind of declarative knowledge about what programming is and what skills it requires. And then there was one basic intervention throughout the week of programming, and that was before receiving help. In the control group, we would just provide the help. In the experimental group, we required them to practice self-regulation by first explaining what they were doing, whether it was working, what they were doing, what strategy they were using to try to accomplish that goal, and whether or not that strategy was working. And this fostered some awareness on their own part of their self-regulation skills and helped them improve their self-regulation skills. And then we would provide help after we had them answer those three questions. And so, again, I'll jump into the bottom line, won't bore you with analysis. On the top left, they were more productive. This experimental group is in green. They finished more of the requirements we gave them, and they finished more of their own self-defined requirements across those 5 days of programming than the control group. So this was on the order of 10 to 20% more, depending on the groups of individuals. In the bottom left, those are the self-defined requirements for their website that they made, so they could come up with goals that they wanted to accomplish and then accomplish them. So they defined many more of their own goals and accomplished many more of their own goals. In the top right, there's self-efficacy, so you can see the control group in red kind of hovers around neutral, marginally above neutral. And then the experimental group was significantly higher, getting almost to positive. They actually believed they could do these tasks. And then in the bottom right, on growth mindset, this was a standardized measure of somebody's theory of intelligence, their belief of where new skills come from. Is it inherent to your biology, or can you actually learn new skills? All of them started off with a relatively positive growth mindset, and in the control group, this rapidly eroded to neutral or negative, which is an unfortunate replication of lots of prior work that shows this happens in higher ed as well. And in the experimental group, we maintained this throughout the week. Just from that simple intervention of prompting self-regulation and giving some theory of what programming is. So Dasana is working now on trying to teach self-regulation at scale through problem-solving work examples that kind of show how experts work through problems now. This is unpublished work as of yet, but probably will materialize soon. So making programs easier to write is partly about teaching programming self-regulation skills. And this promotes independence and increased productivity and higher self-efficacy and maintains a growth mindset, and actually doesn't require a lot of work to achieve. It's almost like you could imagine implementing this as a protocol for TA help, right, in a laboratory. It's just a bigger question around how to scale that. If you're teaching a class in a MOOC, for example, with 5,000 learners, how do you do that? If you're doing this in an online coding tutorial and there is no teacher or TA, how would you promote self-regulation? These are some of the open questions. All right, so what's next for the lab? We've only been working on some of these problems for a couple of years, so this is just the total sum of about 2 or 3 years of effort, Gidget aside, which is a little bit older. What do we want to do next? Got a couple of new grants, so one of them that was just funded out of NSF's Cyberlearning program. This is the idea that in all of this work that we've done and that others have done, we show a lot of increases in learning, but we almost never show mastery. We never show somebody getting every question right, every problem right, everything about a programming language right. And to get really to that higher level of success of learning, you really need personalized content and feedback. You need to build things based on people's prior knowledge and give them personalized feedback about their misunderstandings. And doing that in an automated way and a scalable way is very challenging. So human tutors can provide it pretty well, but we can't scale that yet. So we're building a tutor that really provides an infinite amount of personalized practice by applying a bunch of new techniques from program synthesis and our new theories of programming knowledge. And so we're trying to build a tutor that basically will keep on working with you until you get it. And help you master it, and build really robust statistical models of that mastery so that we know when you've mastered it. This also means actually building much more robust and validated measures of knowledge of programming. So the kind of side effect of this will actually be really good instruments for how to measure this that might generalize to other learning settings such as higher ed. I think that we're on track so far with some of the prototypes that we haven't published yet to kind of promote mastery of CS1 content in just about 10 hours. So that could take a whole course that happens over the course of 500 hours and switch it to just maybe a difficult day or two, right, of hard work. What would you teach in CS1 if all of that stuff you normally teach came for free the weekend before class started? Another grant that just got funded, this is out of a software engineering solicitation at NSF. Self-regulation is really powerful based on some of this work, but it's really only good if you have good strategies, because no matter how much you self-regulate, if you don't have a good strategy for solving a problem, you're probably not going to solve it either. So this is with my collaborator Thomas Latoza, who's at George Mason University. We're defining what programming strategies are. We're coming up with new ways to describe them, to discover which ones exist, when they're effective, how tools mediate their effectiveness, and then finding ways to support people in learning those strategies and executing those strategies. And the goal here really is sort of a new science of programming strategies that's analogous to other disciplines in engineering that have engineering handbooks that kind of codify all of the ways that you solve all of the major problems in an engineering discipline. We think that in software engineering, this is actually really descriptions of how people solve classes of problems as opposed to sort of classes of solutions. So I think this will be an interesting new paradigm for thinking about what it means to be a software engineer and what knowledge software engineers have, and also kind of positions us to kind of create a bridge between novices who are learning a lot of these skills and the experts that have been mastered. One of my students, Kyle Thayer, who did the work on bootcamps, is really interested in API learning. So he's been working on a new theory of API knowledge as kind of three things. Knowledge of the domain concepts embedded in APIs, all of the design templates that APIs use to solve problems with themselves, and then semantics about the execution of the API. So he's working on some techniques to automatically extract a lot of this knowledge from API implementations themselves, so that you could basically take any API source code and generate all of this knowledge, and then build tutors that teach all of that knowledge rapidly, so that you could basically have API learning at scale with no teachers for any new version of any new API that came out automatically. Lastly, I'm doing a bit of work on accessibility with Richard Ladner, and here the question is, how do we teach teachers at scale enough about accessibility so that we can teach all of the engineers in the world about accessibility? Because right now, there aren't nearly enough that know accessibility deeply or even shallowly. So we did a survey and found that for those in the faculty in the room, we probably spammed you at some point in the past 6 months. Most HCI faculty teach accessibility. Few others teach it, but almost all faculty in computer science and information science want to teach it. They just don't know how it's related to their content. They don't know how it's bridging it. So I have a student working on a kind of CS teacher training at scale module that teaches accessibility at scale without having to take a lot of time away from faculty. So there's a lot of interesting efforts here. I mean, mine is just a sliver. There's another 60 or 70 researchers in this space who are really advancing computing ed research in a way that hasn't been done over the past 30 years of sort of 60 papers saying, here's my great new class. We're beyond that now. We're really looking rigorously at sort of the science of learning of computing. And there's a whole bunch of open questions. There's questions about things like, how can people learn machine learning, right? Google cares a lot about this. They have whole 800-person seminars where they try to teach all of their engineers about machine learning, and most of them still don't get it and can't build products or services with it. So there's really fundamental questions around all things that we teach in computing that we still don't know how to teach or help people successfully learn. So there's lots of faculty who are kind of gently pivoting or fully pivoting and really working on some of these problems. I hope some of you will join us. And our doctoral students need tenure track positions to continue their work. So think about making positions for this topic, or at least including it amongst the topics that you think about, because it's a really fundamental challenge that we're facing, I think, as not only university institutions, but also the whole world in trying to help people master a lot of this knowledge. Thanks a lot for your attention, and I'm happy to answer any questions.
how you measure, so that particular topic, I'm always curious how you measured that they learned it.
Yes, this was the summer class of the high schoolers that we were teaching for 2 weeks, right? In that study, we actually didn't measure learning directly. What we measured in that case was we had predefined several requirements that the website had to satisfy. So this was things like your website has to have a profile image in the upper left, right? It has to use this particular kind of jQuery behavior to have something be interactive, right? So we defined, I think, 40 or 50 of those, and their productivity was measured based on their satisfaction of those requirements, and on top of all of the other self-defined requirements that they came up with. So in that study, we didn't know whether they learned it, so the only proxy was that they'd successfully implemented it.
And then just did you check that by eye? Did you run it through a syntax checker?
Yeah, we had a team of 4 undergraduate researchers who carefully read every single line of code that all of those high schoolers wrote. And then redundantly coded it and came up with lots of good kappas and alphas and yes.
Why is the beyond the CS1 level of teaching, like teach some more complicated ideas like recursion or some higher level of structure? Does your theory still hold in that scenario?
Yeah, I think that's a fascinating question that we don't have an answer to. And I think that one way to think through it is to try to take the most advanced things, or the things that are most unlike a lot of the types of basic skills that we teach. So take sort of supervised machine learning, right? So say you want somebody to understand that. What does it actually mean to understand supervised machine learning? I don't think we have a good theory of that, and because we don't have a good theory of that, a lot of the approaches and attempts to teach it to people don't work out so well. So like Google's theory of knowledge of supervised machine learning seems to be, as long as you can observe everything that goes in and comes out of a machine learning classifier, you will somehow magically know how to build them, right? Because all of their instructional technologies that they create for this are big visualizations that just show you the behavior and operation of these. Somehow that doesn't seem to be effective. And yet we don't even have studies showing that they're not effective. So it's just a complete lack of evidence altogether about anything related to those more advanced topics. Yes?
Can you talk about how gender plays a role in your research and kind of how your suggested strategies would help with that gender gap for learning how to code?
Yeah, I think that I think this is a more foundational thing than the discipline and content area of computing. And so most of the research on learning science that looks at gender talks about it as being mediated through things like self-efficacy and growth mindset and other cultural norms that allow people to feel like they can be part of the learning context, that that's where somebody can successfully learn something with their peers and with a teacher. And so when you talk about things like self-regulation, or you talk about some of these other theories of programming knowledge, all of those have to be done in the context of those higher order things, those higher order sociocultural effects that would actually mitigate somebody's efforts in a classroom, right? So suppose we did this great self-regulation instruction in that high school camp, but we also had an instructor that believed in the geek gene, right? That wouldn't have worked. I mean, that's my prediction, that that's going to dominate some of these other effects and interventions from self-regulation, because first learners decide whether they belong, and then they engage, and then they pursue resources, and then they seek help, right? And it's really some of those identity and cultural things that determine other people's learning behaviors and not the other way around. So really, I'm playing in a space here of, under the assumption that we have wonderful inclusive environments, what would we need to promote successful learning? Because we can't have successful learning without some of these content considerations. But we also have to have those inclusive environments at the same time. And I think there's even more great work happening in that space to try to understand what that looks like. The challenge is actually implementing that in practice. How do you change the cultures of high school classrooms? How do you change the cultures of CS departments? And that's a much harder problem, and not necessarily a research problem, right? And that's what makes it difficult to change. Yeah.
So I think there was a slide with Benji Shea doing personalized feedback.
Mm-hmm.
So what is your approach for getting that personalized feedback? Because as you mentioned previously, like a semantic error could be like a result of many different like like thoughts. So like, how would you determine which is appropriate to give as a feedback? Because going further than those kind of basic feedback that things like Code Cognition give.
Yeah, that's a great question. This is ongoing work, so I'll tell you what our ongoing approach is. I don't know if it works yet. And so the idea that we have is to really tie it in with some of these self-regulation skills. So if you're teaching somebody how to self-regulate while they're also learning all of these other basic foundational skills around programming, what that actually means is helping them surface and make explicit to themselves all of the comprehension that they have, all of the strategies that they're using, and so on. So if we can find structured ways of promoting self-regulation in this tutoring environment, then we can observe all of the underlying decisions and beliefs that they're making, and then use that to actually interrogate and give feedback on those decisions that they're making. So a concrete example might be something like, if we're having learners always say, I think this is the place where the program is going wrong, and therefore I'm changing this, then we can actually have some structured representation of their hypothesis, and then we can give them feedback on their hypothesis rather than feedback on their program's correctness, right? So that's the hunch that we have. We don't know if that's going to work out. You know, it was just funded in October, so we've made about 2 months of progress, but that's kind of the direction that we're heading in. Yeah.
Thank you for your talk. I enjoyed it. So you talked about mastery, and I wanted to understand your definition of mastery, because what I got from the slide up front is that mastery is about getting things right. And I want to understand more your definition of mastery.
Yeah. So defining mastery depends a lot on the content area, right? There is a right answer about how a Python program executes. And I think that's unequivocal, and I don't have to defend that because there's a definition of how it works. It's formal, and there's no ambiguity in it aside from the implementation of the languages themselves. And so we can define for somebody's ability to know what a program will do, what mastery is pretty unambiguously. They should be able to take any program we give them and say exactly what will happen, right? It gets a little trickier when you do things like problem solving, right? Write a program, write a chatbot that responds to blah, 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 and gives these kinds of errors. Those are ambiguous requirements, and there's many possible solutions to a program that does that. What does it mean to have done that correctly and mastered that? We're kind of abstracting away from the problems themselves and saying mastery of programming is actually mastery of self-regulation skills, and not mastery of sort of solving certain kinds of problems. But even then, what does it mean to master self-regulation skills? I don't know yet, because we don't have good definitions of what those are yet.
Yeah, I was thinking that from your full presentation, I was like, oh, mastery is about self-regulation and the ability to self-regulate. But in that one slide, it seemed that mastery was about getting things right. So it's...
Yeah. Well, and I think that's a general challenge with anything that you do in learning, whether it's computing or anything else. Trying to define success can be really difficult, because it is a very content-specific thing. It's not really some universal notion of success. And all of those of you in the room that have taught know that when you're trying to define some learning objectives for a class, even defining them is hard, let alone trying to measure them is hard. And so most of the time we just give up and write some multiple choice exams and hope that it roughly measures something, but we have no clue, right?
Yeah, fascinating experiments, and I'm wondering, when you want to measure the outcome of the experiments, of the treatments, what do you measure? Is it long-term learning, short-term learning, or creativity? Because most of the assignments in programming do not target creativity, but in real world we need to be very creative to solve problems in programming.
Yeah, I think that partly it goes back to this question of mastery. If you have a good theory about what some knowledge is, then you have some basis on which to define what that knowledge is and what somebody possessing that knowledge might mean, right? So I would break it down into, knowledge of programming languages we can define pretty well. If knowledge of programming is about self-regulation, maybe we can successfully define that. But there is this other thing, right, that's outside the context of that programming theory that we talked about, which is, what about when a problem has no existing similar solutions, right? How do people come up with novel solutions to things? How do you support that creative process of identifying a novel solution to a novel problem? And I think that's something that I don't know that anybody's really theorized about in the context of programming. We don't really have a firm grasp on what that even means, or how it's different from more routine problem solving. So I think those are some interesting open challenges. And This is, at a meta level, the fun thing about this field, since I've started doing work in it, is that we have almost no answers to anything, so anything you do will probably become seminal work, so get started.
I think that's probably a good place to leave it off. Thank you again.